Okay, this is for Maddie and Teresina. Hi. Okay, consider the reaction. Oh, most important thing, right? What values for delta G are thermodynamically favorable? So when delta G is negative, that means we're releasing energy to do work. Okay, so when delta G is negative, the process is thermodynamically favorable. TFP. That's the most important part. Okay, so what you want to see for your delta G is a negative value. Otherwise, that means that you have to put energy in to get it to do its thing, you know, like baking a cake. Okay. All right, consider the reaction. Calculate the value for delta G and determine if the reaction is thermodynamically favorable at 298 K. All right, so we're calculating delta G. We're given a table of values. We're not given a delta H and a delta S. So this is one where we're going to do the sum of our products minus the sum of our reactants and figure out if it's negative or positive. Okie dokie. You'll also notice anything that is in elemental form for delta G, the values are 0. So you can just leave those out of the equation. So we have 2 times H2O plus 4 times CO2 plus 2 times N, which is just 0, so we don't have to worry about that. Okay, and then minus the delta G's for our reactants. So 4 times HCN. And then O2 again just has a value of 0, so we can leave that out. And I get a value of negative 2536. Let's look at our units. Kilojoules per mole. Okay, we have a negative value. So are we thermodynamically favorable? Yes. Okay. Okay, here's a good one. When calcium chloride is added to water at 298 K, it dissolves and the temperature of water increases. So write the net ionic equation that describes this change. So it's a dissolution equation, right? Calcium chloride. Are you guys in the right class? I feel feel like you have that look of like freshmen that are sitting out and they're like, oh wait, I thought this was religion. Huh? You guys are okay? Elena keeps giving me weird looks. She's like, I don't think I'm in the right classroom. Now, is this your, it's AP. You think him? Yeah? Okay. Alright. Just making sure. Okay. CaCl2. Solid. When it dissolves, what do I get? Ca plus 2, that's right, Audrey. Look at you go. And?
2 Cl.
Yay! 2 Cl minuses. That's right. Good jobbers. Okay, predict the sign for delta H. So what's happening with our heat?
Increasing. Like it's going up or something.
Well, think about it. You've got this stuff in water. The water is our surroundings.
So it's taking it away from it.
Yes. So if the temperature of the surroundings is going up, the delta H is negative. Right? The dissolution of the calcium chloride is releasing heat. The water is the surroundings and it's absorbing the heat. So delta H is negative. Okay? What's happening with our entropy? It's becoming, it's dissoluting. I don't know if dissoluting is a word, but we're going to use it because I like it. Dissolving, I think is the word. Because we have our compound, right? It's breaking into its ions. So you're going from one part to more parts. Anytime you think about that, you can think about an increase in entropy. So our delta S is positive. Okay, so both of these values are thermodynamically favorable, right? Okay, so what do you think we should predict about our delta G?
It's gonna be negative.
It's going to be negative, right? So if both of these things are thermodynamically favorable, then our delta G will be as well. Yay. Okay. Is everyone comfortable with our predictions for delta H, delta S, and delta G? Callie, are you in the right? You're in the right class? Okay. Do you ever have those dreams? I still do at my age, where I'm wandering around either my high school or my college, and the bell rings, and I'm like just standing in the hallway because I have no idea where to go. Nobody has like anxiety dreams like that?
I mean, I have anxiety dreams, just not.
Like I stand there and I'm watching everyone like rushing to where they're going, and I'm like, I don't know. It's very scary. Okay.
I went to the wrong class like last week.
Do you ever have the tooth dreams? I always have dreams that I lose my teeth too. Ugh, scary. So scary. Okay. Alright, so here's our reaction. P4, blah, blah, blah. That doesn't matter. Calculate the value of delta S for this reaction. Okay, we're given a table of values of our delta S's. So what we're going to do is products minus reactants to figure out delta S. Okay, so P4O10 minus P4 plus 5 O2s why 3 decimal places? I get negative 961.19 joules per mole K. Anyone else confirm that? That's what okay. All right. Is this reaction thermodynamically favorable at 298 K? So we have a delta S, we have a T, and we have a delta H, right? You guys see that? We have delta H, delta S, oh, and our T. So we can plug that into our Gibbs equation. So delta G equals delta H minus T delta S. Okay, so this is an example of where I said make sure our units match. Okay, because look at our units for delta H, and then look at our units for delta S. Okay, so our delta H is in kilojoules, and our delta S is in joules. So I always, because most delta G values that you're given are given in kilojoules, I always change my delta S to kilojoules. Okay? So if I wanted to change this from joules to kilojoules, which way would I move my decimal point?
To the left.
To the left. How many spaces? 3. So I would get negative 0.96119 kilojoules per mole K. Okay, so that's what I meant about making your units match. So my delta H is negative 2984 kilojoules minus 298K times negative 0.96119. What did I do? So negative 2984 kilojoules plus 286 kilojoules per mole. Negative 2698 kilojoules per mole. Or you could just put kilojoules, that's fine too. Okay, so we got a negative value, so what does that mean for thermodynamic favorability?
Favorable.
Thumbs up? Yes.
So delta S is negative, so that wouldn't be GSP, but because delta H and delta G are negative, it's okay.
Right, so if you were to go back to this chart, right? In the first row, right, when delta H is negative and delta S is positive, right, you're going to have a thermodynamically favorable process no matter what the temperature is, okay? And it's all based on mathematically that Gibbs free energy equation. If you have a delta H that is positive and a delta S that is negative, right, you can never be thermodynamically favorable. The temperature wouldn't matter, wouldn't have any impact on it. Okay, but the one that we were just looking at, they were both negative?
Yeah.
Yeah. So delta H less than 0, delta S less than 0, right? Those can be thermodynamically favorable at low temperatures. And then vice versa, when delta H is greater than 0 and delta S is greater than 0, that can be thermodynamically favorable, but with high temperatures. Right? That chart is really difficult to understand, but it can all be figured out mathematically, which is always my preference anyway. So in this case, we had a negative value for delta H, yay, that's TFP. But we had a negative value for delta S, which would normally be a thumbs down, right? But because that 298K, right, kept, how to explain? If it was a really high temperature and this term ended up being greater than this term, then you could still then it would no longer be a negative value for delta G. So it's like mathematically, if you don't have both terms being thermodynamically favorable, what can that temperature term do to push it over into the thermodynamically favorable calculation value? Okay. So here's a good example to look at after we just talked about that, right? So when is a reaction with a delta H negative 10.6? That's a pretty small negative value for delta H, right? And delta S is negative 261 joules per mole K. When would that be spontaneous? All temperatures, no temperatures, high temperatures, low temperatures. That rhymes. It's like a poem. Yes. Is that
If you do no temperatures, would it just be times 0?
negative 10.6 minus T, and remember this has to be negative 0.261. It would have to be really low. Yeah, so that this term would not be greater than that 10.6. So it would have to be very low temperatures. Is that what you said, Elena? That's impressive. I could not figure that out without looking at the math first. So, way to go.
Doesn't
What?
it tell you on the chart though? It says if delta H is less than 0 and delta S, then.
You should know by now that I don't have things memorized. Come on. Let's see. Delta H negative, delta S negative. Yeah, you're right. Look at you. Look at you go. Okay.
The temperature would have to be lower than 40.
Which, lower than 40 Kelvin. I don't even want to think about it. That's what everyone keeps telling me it's going to be like when we go to visit Syracuse.
I mean, let's see what the temperature is in Syracuse. 298 is 0 degrees Celsius, right?
Yeah. So what's 40K? Minus 273. It's fribbin'.
What day are you going?
We'll be in Syracuse next Monday and Tuesday.
It's negative 387 degrees Fahrenheit.
Yeah, every time I look at the temperature, it's
don't
like
think
the
it's
same.
Maybe the feels like is 30.
Thursday, the high is 47. Like this Thursday. So 40 Kelvin in Fahrenheit is negative 387 degrees.
Yeah. So when you have a delta H, I don't know. This would be very unlikely. Like you would have to manipulate the temperature, put it in like liquid nitrogen or something in order to get it to actually happen. Because What did you say? Negative Fahrenheit was 300 something?
387?
Yeah. Like, we wouldn't be alive. Okay, so that's delta G, that's Gibby. Those equations, both of those equations are on your equation sheet. Okay, delta G, both of these two, boom and boom. So, not much to remember there other than that negative delta G is thermodynamically favorable, and make sure that those units match when you plug into the equation. Okay. All right. 9.4. We're moving.
How many do we have?
Does it go to 911? Okay. All right. Thermodynamic and kinetic control. Thermodynamic, kinetic control. Okay. 9.4. Hoping we can get through 9.6 today. I think we can do it because these are quick.
I believe in it.
All right, so many, just because something is TFP, right, does not necessarily mean that it's going to happen instantaneously. Think about carbon turning into diamonds, right? Everyone's like, oh, well, if it can happen and it's thermodynamically favorable, which that is, they're like, why can't we just crank out diamonds all the time? Well, because they are something that takes, I don't even know how long it takes. Thousands of years? Millions? Who knows? But many of our thermodynamically favored processes do not proceed to a measurable extent, or they occur at extremely slow rates. This is known as being under kinetic control. Okay, and the reason for something being under control generally has to do with having a very high activation energy. So this reminds me of, actually reminds me of the Boston Marathon. How do you know if someone's run the Boston Marathon? Don't worry, they'll keep telling you about it. Don't worry. But the marathon itself is a net downhill. Okay, so Elena Pig, if you hear that a course is a net downhill, generally you're like, oh yeah, right?
Yeah.
But what they don't tell you is in the middle of that 26 miles of net downhill, there are hills that are like, right? So you could have a reaction that is a net downhill, as in going from higher energy to lower energy, right? But what if there's this ginormous hill in the middle of that process, okay? So the Boston Marathon, even though it is a net downhill race, it is probably the hardest race on the planet because of what is in between all of those net downhills. The same can happen with a chemical reaction. So technically, based on its kinetics and its thermodynamics, right, it's likely to happen to go from reactants here to products here, right? But if you have that ginormous hill in the middle, which is your activation energy, it's going to happen at a really, 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 really slow rate, or almost seem like it's not happening at all. Okay? Okay, and here is a good piece. I think this is straight from your I do, we do, you do, right? Some reasons that reactions with a negative delta G do not occur may include that high activation energy, unfavorable orientations of your particles, or a large number of particles that have to collide simultaneously.
So collision theory.
Essentially, collision theory being unfavorable. Yeah. I like that you're bringing up collision theory. Okay, and this is the difference between kinetics, which I think you guys loved our kinetics chapter.
What unit was that?
Was that a sneeze? That's a cute one. And thermodynamics. Okay, thermodynamics, what we've been talking about this unit, delta G, delta H, delta S, is will the reaction occur? Okay, kinetics, remember, tells us how fast it will occur. Yes, yes. Like if you go out to a 5K race, and you've got Anna Bacchius out there running, okay? But then you have someone's grandma with a broken ankle, you're gonna think grandma is not even competing in the 5K compared to Anna Bacchius, right? Yeah. But she is. She's out there. She's on the course. She's moving along, but she's just not really moving along at a measurable rate. You're like,
Why is she moving along? Why is she out there on the course? Those are
Should be on the sideline cheering.
maybe
for
the
her.
5K was for a cause that was near and dear to her heart, like elderly women with broken ankles. We have rights too.
Where do they run the like Wilmington?
The Wilmington Marathon?
Yeah, because I saw like all those signs where
It starts down at the riverfront, and then it runs down into my neighborhood, and then it goes back to the riverfront, and then it finishes on the Markel Trail, like out towards, running out towards Old Newcastle. Do you know the new trail out there on the riverfront?
Interesting.
Yeah.
I was curious because Wilmington's not like that.
Well, it used to be 2 loops. It always used to be 2 loops of the same thing. I will never do a multi-looper marathon. That, I feel like that is just like a mind game. You're like, oh, there's the Walgreens again. Especially 2 loops when it goes in my neighborhood, I would just be like, peace out, I'm going home. Yeah, I don't like those multi-loop marathons. Do you know, I mean, the Olympic marathons are usually like 10 loops of the same like 2.5 mile course. I mean, that is torture. But now, since they have built the Jack Markell Trail, they now do the 1 loop, and then the half marathon finishes, and then the full marathon goes down for the rest on the jam.
Is that the trail with the bridge over the Christina?
Yeah,
The new one.
yeah. My husband designed that bridge. Did you know that?
My boyfriend and I put a love lock on that bridge.
Stop. You put a love lock on my husband's bridge. Michael Campbell designed it.
Noodles always tells me that. She's like, oh, my dad designed that bridge.
She does. I know. She's so proud. He got to be there because he built a boat. Did you know he built a boat? He built his own boat.
Didn't it sink though? And then he
Yeah, it did. But he got to go out on the river in his boat when the crane came in and dropped the pieces of the bridge down. Like he was
That's
sitting
so
in his
cool.
boat watching them like drop the bridge pieces down and like fit it together. That's pretty cool. Okay. So this is all there is to 9.4. So let's take a look at how it shows up in problems. Okay. All right, the reaction for iron with oxygen to form iron oxide is shown. That's rust. That's rusting. Calculate the value of delta G for this reaction at 298K. Okay, so we're going to use Gibby. Gibby. Delta H minus T, 298K, delta S, but we need that in kilojoules, right?
Yeah.
KJ. Woo, God bless you.
Thank you.
And I get negative 1486 kilojoules per mole. Kilojoules. All right. The reaction is very slow at room temperature, but is much faster when you add water to the reaction. So very slow at room temperature. Why would that, what would be a good reason for that? Well, we could, because our delta G tells us that it's thermodynamically favorable, but as soon as we hear that something is going very slow, we immediately want to think under kinetic control. Okay, and let's propose a reason why it could be under kinetic control. I'm looking at the molecularity of our reactants. Like we have 4 particles of oxygen that have to collide with 3 particles of oxygen to produce what we're producing, right? The molecularity, you could say high activation energy. You could really propose any one of those ideas. Okay.
Are you saying that it's like the molecularity plays a factor because at a gas it's harder for them to collide because they're all spread out more?
Yeah, and you're really looking at 7 particles that need to collide effectively. But you bring up the idea of getting the gases to collide. How might adding water help facilitate that?
It's more compact.
It's-
so it's like easier for them to. They're more likely to hit each other.
Correct. So it's kind of allowing those gas particles to stay dissolved long enough to help them more effectively collide with. So allows for so H2O allows for the gas molecules to more effectively collide with the iron atoms. Okay, sketch an energy diagram that shows both circumstances described in part B. Right, so for my first, well, our delta H was negative, right? Yes. So that means our reactants are going to be higher than our products, okay? But how should I make the hill in the middle look if we're talking about something under kinetic control? Right, so even though, just like the Boston Marathon, even though we have a net downhill, we're going to have a big hill for our activation energy in the middle there, okay? The water in this case could effectively act like a catalyst, so really all you would have to do for that is I would just draw it in with a shorter little hill there. Okay, so D is a good question. What happens to our delta G when the water is added? Right, no change. Because remember, right, our delta G is based on this here. Delta G, delta H. Right, our delta G is based on thermodynamics. What's happening up here is our kinetics. Okay? So even if we're able to bring that little hill down, that has no impact on our overall value for delta G.
Oh, you're saying delta G is the x value, so it doesn't matter. Keep bringing it down.
Delta
Like, if, like it's on the x axis, like if you were to read it.
No, I mean, for these energy profiles, right, this is the course of the reaction or time, if you want to think of it. And then on this axis is your potential energy. So that's still technically a y-axis value. All right, so see if you guys can figure this one out.
No, it's definitely negative. Look at yes, I think they're all negative.
It's favorable.
It's favorable delta S. No, they can all be negative. Well, it is that. And the other one, what did she? No, I don't know. No. But you know, another time, negative delta H is
It says temperature right there.
Delta S is positive delta S.
It's not a low temperature.
Okay, so what do we know about delta S? What might we base that on?
I said it negative because it's being combined.
Correct. So we're going from 2 moles of gas to 1 mole of gas. So delta S would be negative. What about delta H?
Negative.
Delta H, negative. What about delta G?
Negative.
Thermodynamically favorable, yes. Provide an explanation for the fact that this reaction does not occur at room temperature, but does occur as the temperature is increased.
Could it be something to do with the gases, so that if you increase the temperature, they'll have more like energy, so they're more likely to collide or something?
Exactly right. So temperature is a measure of the average kinetic energy of our particles, right? So more temperature means more kinetic energy. For the gas particles, right? Which always leads to an increase in our effective collisions. Okay, is everyone comfortable with what we just did? 9.3, 9.4. All right, let's take like a 5-10 minute break before we tackle 2 more sections, okay? We can do it, right?
Miss Campbell,
Yes.
could you record on Tuesday and Wednesday as well?
I think so.